Okay, so let's start our third talk. Mr. Yiheng, a PhD student from University of Hong Kong. So he will talk about teaching language model to understand the visually read documents.
Okay, so thanks for the kind introduction. So I'm Yiheng Xu. Thanks for everyone for coming. So today my talk is about how to teach language model to understand visually rich documents. So I know that most talk in this conference is more like theoretical. So my talk will be quite different because my talk is in the big data technology track of computer science. So I will present my work more like on the application side. So hope you enjoy it. So let's get started. Okay, so here is the overview of today's talk. Basically, I will introduce the research work that we did, LayoutLM, pre-training of text and layout for document image understanding. And also I will introduce the follow-up research work. So most of this work were done during my internship at Microsoft Research. So yeah, during the 1-year undergraduate internship, I tried to solve the problem of how to teach the language model understand visually rich information. And also I would like to use the remaining slides to maybe share my recent effort and thoughts about this direction and how can we push the boundary of this direction to another level. So let's get started. So at the very first, I would like to share some examples of what is visually rich document, or AKA VRD. So visually rich document is it includes a lot of text, and also the text is in rich text format. So basically, these are some examples like the scanned documents and the digital born PDF, and also HTML web page is also visually rich document. So this document is really important, and for a language model, it's hard to encode because the language model can only accept text or language. But if we want to teach the model to learn to encode more information, we should design more architecture and some tasks to help the model understand it better. So these are some representative tasks of visually rich document understanding. So the very simple one, document image classification. So given a PDF like a financial report, the model need to classify this image as with some labels, like the financial report. And also something like information extraction, document information extraction. So given a very complex document, maybe a form or a scientific report or papers, the model needs to somehow extract some meta information like the maybe k-value pairs or some other structured information. And also the web page, another one is web page information extraction. Similarly, the model needs to extract some predefined schema and extract the k-n value to make it as a structured knowledge. So this task is kind of simple but really important because these are crucial tasks to build maybe knowledge base or knowledge database, and further it's a very fundamental task to help us do some further analysis for large scale data. So, and we can see that for this task, visual information is really important. So traditional method maybe usually use model the document image as a sequence of text tokens. So we can OCR the document image and get a sequence of text and use some NLP model to do information extraction or something else. However, we could find from the example that a document contains not only a series of text tokens, but also rich visual information. So for example, for the fine-grained feature, we have some spatial, very important spatial position information. Like if we want to extract text key value pairs, it's very intuitive that the key and the value should be very near to each other. And also another example is table. So table is kind of like a grid distribution. So these are very obvious, a very important feature. And also the font size is very important. You know, like the title and the body. The font size of title is very different from the font size of body. So these are fine grain feature. And another important level is coarse graded. So if we sometimes if we want to do task like classification, we don't have to read word by word. We can just see the whole overview of the document. Like so, we call it document layout. So like for example, the poster and a form is quite different between each other. So it's very easy to classify this document. And also the charts or images are also important features. So for example, if we given a document, we can ask the model with a question like what tobacco brand of GPI is showing the picture. And the model need to actually read the image to understand this question and give the correct answer. It's impossible to like only rely on the text to solve this problem. So these observations make us to think about this problem, and so we present the first paper, which is the research work got award in this conference. So the title is LayoutLM, Pre-train of Text and Layout for Document Image Understanding. So yeah, so this is the overview of our model. So it's kind of complex for these slides, but I will introduce step by step. So basically we try to extend position embedding of a bird model to a 2D position embedding to model the spatial position and the size of word. So you know, so as we discussed before, we can actually use some OCR tools to extract the text and the layout. The layout means the coordinates of each word. So we can get this information. So the text is the text information, and the spatial information is from the coordinates. So we can actually encode the coordinates as as the position embedding, and we call it 2D position embedding, to align the layout information and text information to modeling this problem. And after to pre-train with some pre-train tasks, we can make the model very good at representing the document image. So here is the 2D position embedding. So the upper one is the bird model, which is a very famous model. We actually there is a 1D position embedding to model the word position in a sequence. We add 2D position embedding to the input embedding group. So the 2D position embedding aims to model the relative spatial position in a document and embed it into language representation. So here is the 2D position. And another important one is the image feature we mentioned before. So to utilize the style feature of a whole document and align it with the text, we also add an image embedding layer to fuse image feature into language representation. So here we actually add an image encoder to extract the image feature and combine with the LayoutLM embedding and do the downstream task. After we change the architecture, we need some pre-train task for LayoutLM to help the model learn how the relationship between different tokens. So for the pre-training task, we use the popular mask language model to predict the mask tokens given the contextual text information as well as the layout information. So in this way, the model needs to predict the masked word based on the given context and the given layout information. So it actually helps the model to learn the relationship between different words. And we use large-scale data to pre-train the model. actually we use like 11 million scanning document image from a large document collection to do this to do the pre-training stage, and finally we get a pre-trained model. And we evaluate our model in three real-world applications, like the form understanding, like receive understanding, and document image classification. So these tasks are the actually product application in the Microsoft. So I will give the form understanding with LayoutLM as an example. So for the form understanding, the problem is to extract key value pairs from documents. So the problem is formulated as a sequence labeling task, which is a very traditional NLP task, and the model will predict the start and end position of the key and values. So after the model predict the start and end, we can actually extract the key and value pair from the output and to extract a list of key value pairs. So here's the result. We surprisingly find that the performance is much better than the text-only model. So with the text and the layout information, for same model size, the LayoutLM-based model is much better than the text-only model. And after we incorporate the layout and the image feature, the performance is much better. It also get better. So another task is the document image classification, which is a very simple one, like the ImageNet. We need to the model needs to classify the input image with a label. And here we can find that after incorporate the layout information, the performance become better with compared with the text-only modality. And also after we incorporate the image information, the performance become much better because as we discussed before, the whole overview of document layout is very important and very efficient for document image classification. And we also do some scaling in this model architecture. So here we observe that the performance of downstream task scales with the amount of training data, obviously. So it's a power law. So this is so our paper is in 2019, and so this is very similar to the current scaling law conclusion, which is widely considered in the current large language model pre-training. So here is a summary. So actually, for the LayoutLM, we create this architecture to build to provide contextual text and layout information in a single framework. And with the pre-training task called mask visual language modeling, we actually get a very surprisingly good result compared with previous state of the art on different tasks. So that is the first research effort we made before. So after we build this work, we try to further push the boundary of this model. After we rethink the model architecture, we find that the image information need to be further explored. So this is the follow-up work of our first model called LayoutLM version 2, which is a multimodal pre-training for visually rich document. This work is also presented at ACL 2021. As we can see, the pre-training of visually rich document LayoutLM is the 2D position embedding for contextual layout information is very effective. However, we use the image feature at the very last of the architecture. Like it's a late views visual information, which that not appears in pre-training. So we are seriously considering to use the visual information during pre-training. And hope we can get a better performance. And so here is our goal. So towards multimodal pre-training for visually rich document, we need to change the architecture to actually provide contextual text, layout, and visual information in a single framework. And also we need to design some pre-training tasks to make the to help the model to do the cross-modal interaction and alignment to help the model learn the representation. And here is the LayoutLM version 2 model architecture. So the most important one is there are some important improvements. So the first one is we actually use the visual encoder and visual feature during the pre-training. So here you can see that the visual token are from a CNN-based encoder as a visual feature, and then we will. So here we combine the text, visual, and layout as unified input. So in this way, we got words and the corresponding axis-aligned bounding box from the OCR result, and the bounding box identifies the spatial position and the size of each token. So we use its embedding as the layout embedding and combine all of them to help the model learning. So beyond and for the model architecture, so here is the encoder with spatial aware self-attention mechanism, which is a naturally extended mechanism we proposed from some existing work. And here is the detail. So the self-attention mechanism make a weighted sum of all input sequence feature to get an updated representation. So the weight is actually the relevant distribution between the target feature and all feature. So we call the weight as the attention score, which is AIG. So here the vanilla self-attention get the attention score by directly calculate the relevance. And the famous T5 paper provide a self-attention with relative position bias. So they actually add a bias term to represent the semantic relative distance in the input text sequence. So based on this previous work, we naturally extend the architecture to spatial aware self-attention. So you can see the blue one. So here we incorporate the spatial relative distance between, we try to model the spatial relevant distance between tokens in the whole document. So in this way, the self-attention model can not only leverage the semantic relative position, but also the spatial relative position. So we try to encode the spatial information in the powerful self-attention mechanism. After the architecture improvement, we propose some pre-training tasks to help the model learn during the pre-training stage. So the first one is very similar to the previous mask language modeling. So here is the mask visual language modeling. So actually, we mask the image and ask the model to predict the image based on the context and layout information. And the second one is text-image alignment. So here you can see the right arrow. So here we actually want the model to learn the fine-grained text-image alignment on spatial location. Basically, we try to mask the words in the image, and on the image side, and on the text side, we ask the model to predict if the word is masked, so covered. So in this way, the model can actually use the layout information between text and the image to learn the fine-grained text-image alignment on with this spatial information. So yeah. So for the third task is text-image matching. So here we actually want the model to learn the coarse-grained text-image alignment on document content. So it's a very straightforward task. We randomly replace some of the images and the model output, whether the text and the image come from the same page. So basically, this task is broadly used to align different modality based on their content. So the negative example should be random images with the text, and the model needs to predict if the image and text are matched. After we do this improvement, we actually pre-train the model on large-scale document corpus. And here we introduce and evaluate our model on a new task called DocVQA, which is kind of like visual question answering on document image. So we have introduced this example in the previous slides. Basically, the model needs to understand the image and answer some questions. And here we can see that with the image feature after combining the image feature, text feature, and layout feature before we pass them into the model, the performance is largely better than the version 1 model. And after we do some data augmentation, we actually got the state of our performance compared with the leaderboard. So the top one of the leaderboard is actually from 13 models in symbol prediction. So with our model, we only need one model to get this result. So here is the overview of the LayoutLM version 2 model. We changed the architecture of our model. The model can provide contextual text, layout, and visual information in a single framework. And also we propose a spatial aware self-attention mechanism to make this happen. And with 3 different cross-model interactive and alignment tasks, the model can actually learn a very good representation during pre-training. And here is the result, and we can see that beyond the DocVQA performance, DocVQA benchmark, we can actually get better performance on all of various tasks. Yeah, so that is the version 2 paper. So we talked 2 papers about document image, and after that, I start to think about how to further extend this direction to more different data from it. So here is another one called Markov language model. It's a web information extractor. So you can see you can actually think about different types of data. A document image is visually rich document, and the HTML is also visually rich document. The HTML is actually rendered by the browser, and we can get a lot of different visual feature from the rendered image. So we start to think about how to extend the model and method to different domains. Extracting extracting structured information from web page is also important, like the document image, because it's a critical task for large-scale knowledge-based construction. There are so many different knowledges on the internet, and it's a very common requirement to extract some metadata from the web page for some search engine company. So as well as Microsoft Bing. So we try to solve this problem, which is we also want to have a model to extract some metadata based on predefined keywords. So there are some challenges in this field. So the first one is previous work often rely on expensive and unreliable features. For example, previous work focused on exploiting visual patterns with expensive render process. So as we discussed before, HTML is actually a document, and when we browse the web page with a browser, the process is like the browser gets the HTML and render the text into a visually rich document. However, it's very expensive to do this process. And another challenge is that another drawback is that the modern adaptive web page are usually adaptive, making the visual feature very unreliable. Here is an example. If you visit a same web page with different device, actually the visual is the visual information is very different. Like if you use mobile, tablet, and desktop to visit same web page, but actually the HTML content is same, are same. Yeah, so that is another problem. And another problem for the previous work is actually they only use a simple classifier with no contextualized feature like globe or word embedding at that time, like 2020, 2021. So we want to use pre-trained model to further boost the performance of this task. So here we start to think about what is the key difference between the HTML and document image. And the answer is the source code of web page HTML. So HTML, aka hypertext markup language, is a standard markup language for documents designed to be displayed in a web browser. So it's a markup language. So there are some different language like markup language like HTML, XML, and LaTeX we use. So yeah, so these are markup language, and which is very different from document image. And there are DOM tree and XPath in the HTML. So DOM tree is a tree structure, is easy to understand. And XPath is actually a query language for somehow select nodes from DOM tree. So on the right side is another example. So if we have a XPath, we can actually select exactly only one node from a tree. It's a query language. So it's very so currently we can see that the XPath is very similar to the coordinate of words in document image, which can represent the single node or words. So if we can use the XPath as a feature and combine this feature with each word, so we can explore if the model can actually use this structure information to do the task we need. So here we try to propose markup language model. It's a pre-trained language model for markup language. We introduce new models and which called XPath embedding, and we propose 3 objectives to train the model. But the most important one is the XPath embedding component. So here is the XPath embedding. We discussed that the XPath can be the only can correspond to the only words in a document. So we can given an XPath of the ith token xi, the target list can be parsed into a list. You can see the whole process in the image. So we can split the XPath expression in different level, and we can separately encode the text and the level as an embedding. And we can combine this embedding and use a linear projection module to transfer the embedding into a feature. So this feature can represent the structure information or the location or the node location in this tree. So with this feature, we can actually combine this feature with the word feature, and so the word feature can get the spatial information. So after introduce this design, we actually we also use common crawl as a pre-trained corpus, and there are like 24 million English web page in this pre-trained corpus. After pre-train, we evaluate our model on some web information extraction task. So here is one example. So the web-based structure reading comprehension basically answer some question based on the given web page. So each question requires a certain structure understanding of a web page to answer. Like the answer should be from the HTML or yes or no. So it's so compared with the previous work, we can see that we only use text and HTML, and we don't need to render the HTML as a visual, screenshot. So with only text and HTML, after the training, we got surprisingly better result compared with the previous method. So which demonstrate our effectiveness. Yeah, so that is the markup LM, the web information extractor. So now we have a document. We have done solved somehow mostly solved the document image and the HTML information extraction. And now we start to further think about how can we understand the visually rich document and try to learn the representation without so many supervision. So here is a follow-up work called DIT. We try to train the model to understand a visually rich document through images only. So, so here is an overview of our learning framework. So basically there are two stage of this of the learning framework. The first stage is discrete VAE training. So basically, we want to learn an image tokenizer, and the second stage is like the pre-training one. So image tokenizer is trying to tokenize an image into a sequence of image patches. It's very similar to an text tokenizer. So text tokenizer tokenizes the whole document into words, and the image tokenizer tokenizes into patches. So after tokenization, we can actually do very similar pre-train tasks like so for the language model we have mask language modeling, and so for the image data we can actually do some mask image modeling after tokenize the input data. So that is a basic idea. So specifically for the stage one, we want to firstly learn the visual codebook, which is we call it tokenizer. So so let X denote the original images and X type the mask image and Z the visual tokens. We actually want to to learn this object to help the model obtain visual tokens and decode. So based on the right side, you can see that the tokenizer actually tokenizes the image into discrete tokens, and the decoder will use the discrete tokens to reconstruct the image into the original one. And the loss is actually the distance between the input image and output image, or the reconstruction. So in this way, we want to learn the visual codebook of the embedding tables. And after we got this, we can tokenize our image well. So here is a comparison. So we want to compare the tokenizer performance on the visually rich document. So on the right, on the left is the original image we input into the model. So the resolution is kind of vague, but you can see that the original image is the is the clearest one. So after reconstruction, we compare our DVAE tokenizer with the OpenAI tokenizer from OpenAI DALL-E, and you can see that the OpenAI DALL-E tokenizer it was trained on natural images, and the images on the right side is not very clear, is kind of vague and not sharp. So the reconstruction from our model is more is clear and sharp, which is a very which is a better choice to help us tokenize the images and help the model learn efficient representation. So after we got this tokenizer, we do the stage 2, which is a mask image modeling, very similar to mask language modeling. So basically, we want to recover the original image from its corrupted version. So we randomly mask the image patches and ask the model to predict the index of the visual codebook. So the model will try to learn the object that recover the visual token based on the masked image, which is actually exactly our mask image modeling prediction task. So the experiment section. So DIT on the document image classification is actually we find that it's very good at do the classification task because it's a vision prediction model, and because it is prediction on the document image corpus, it's very good at this task compared with some previous previous work. And also, this model can actually be a visual backbone for some more complex tasks like document layout analysis. By replacing this model by replacing the original somehow like ResNet in detection framework with our model, we can easily get better performance with our prediction model as visually backbone. So after we released this work, we actually found there are so many different interesting work in this direction. So for example, here's a research paper called Language Modeling with Pixels. It tried to explore more about how to learn language model with visual information, which is actually very similar to how humans learn language. And also another work called Improving Language Understanding from Screenshot. They further use more textual information to supervise the language understanding with screenshots. So that's all about the research work, and here is the summarization. So after we in the visually rich document understanding, we try to build some models to solve different data types. And after we release this model, it actually gets very popular in the research community and the industry community. So the model family has been downloaded over 116 million times and serve as a basis of research and applications of different company and startups. So after this work, I finished my internship at Microsoft and started my PhD study. I try to think about how to what is the future of this work, because LayoutLM and this model are very a good task specific model. And after that, in 2023, ChatGPT was released, and it fundamentally changed the research and applications of artificial intelligence. It's a very good general purpose task solver or problem solver. So I start, and it actually can understand the document image and do some question and answer. So I start to think about and how these techniques can contribute to the progress of artificial intelligence or language model. So we start with the scanning document, and we train the model to understand this this textual, visually rich text information. And then we move to the HTML. The core difference is that the HTML or the web page is interactable. So we can actually call it web browsing. So I start to think about that. What if we extend the web page to operating system or computer, or so computer is a very general visually rich human interface that require both understanding and control. So current model, including ChatGPT, are very good chatbots. But this model cannot take action. If the model can take action and control the interface, like what we do, we can actually, the model can actually do a very so many different tasks for us to implement digital automation. And also, um, with with so powerful reasoning ability like ChatGPT, the model can actually become an autonomous agent model. And eventually, if the model can actually use the computer to learn knowledge and get feedback from this environment and self-evolve and become better and better and surpass human ability. So so currently I'm trying to extend visually rich document to human interface controlling. So we call this computer using agent. So there are some initial work in this direction. And here is a famous work called Web Arena, which they try to build a web browsing agent with large language model. And the model can accept a high level or complex goal. And the model can use the keyboard and mouse to control the web browser and finish a very and try to finish a very complex task. But currently, we find that this task is very different, and the performance is super low. So it's a relative new direction, and we need more research work to make this happen. And I would like to share some very initial work after I started my PhD. So, but this topic is far beyond today's topic, so I will very briefly introduce its work. So this work called OS Word, which it's about benchmarking multimodal agent for open-ended tasking real computer environment. So basically, we try to build a operating system environment to and ask the model to do some open-ended tasks. And the model needs to do very complex multi-step reasoning and grounding or take action to finish this task. And we have some evaluation script or matrix to evaluate the ability. So so this is OS Word. And also we try to do some research on the model side. And this is a research work at iClear 2024. We try to analysis the natural language ability and code ability of language model for language agent. So we try to prove that program language is a very good action representation for language agent to control the environment. We actually train a large language model with like 70 billion and from Llama 2 and build a language model called Lemur, which is very good at both natural language information, natural language ability, and code ability. And we prove that on so many agent scenario and agent ability, like use some tools and self-debug, follow feedback from the environment, and explore the operating system environment. The model can actually performance much better than the Llama 2, only because the model have a more powerful coding ability. So that is the model side. We try to explore how we can build a computer using agent in environment. So yeah, so that's all about my recent effort and thought. I hope you enjoy this talk, and I welcome any question. Thank you.
How you talk? Anyone have any question?
Very good talk and a very good package. Actually, we use this package to process the recipe and so that you can do the question answering based on the recipe. But the receipt, not recipe, receipts.
Okay.
My question is like for this work, you cannot take advantage of large language model, right?
Yeah.
Basically, you rely on the training data set you have. You cannot leverage the pre-existing huge amount of text data.
Yeah.
On the web. Have you thought about how to combine what you have developed with those large language models, like Lala kind of architecture, so that not only we can rely on the training that you have, you also can leverage a huge amount of data that already exist in
Yeah, so yeah, a very good question. So currently, there are after the LayoutLM model family, there are many like OCR-free research work to try to solve this problem. Yeah, but they yes, they rely on the document image and text revision to ask model to do this process. But I think so at that time, like 2019, so it's very hard to do this end-to-end task. But currently, with the scaling, after scaling the model size and the training data, this can be a very simple task and very simple pre-training task to make it happen. And fortunately, we can actually build large amount of like document image and text very easily because we can just render the text with some tools and get the document image. And so this we call this synthetic data. So this is a very basic. We can build large. We can build large amount of data to make this happen. I think so. Currently, I think Lava can. So the model architecture like Lava can use this synthetic data to make it understand high resolution document image.
Do you see any comparison with this kind of architecture with your algorithm? Certainly, I would hope that your algorithm will win, right? Because we benefit from your tools and
thank you.
But now there's a new architecture there, not new, but it's a kind of multi-modality model. You can take advantage of both image and text.
Yeah. So so for our algorithm, it's not like a end-to-end like architecture because we rely on the OCR tools to extract the OCR and layout information to make this happen. I think so. I think ideally an end-to-end modeling is a very good architecture to make this happen. So currently, so for the computer agent, I am also trying to like build my agent with pure vision architecture. So we want to train the model to only like depends on the image screenshot, the desktop screenshot, and do some tasks instead of do some like OCR pre-processing. Yeah, thank you.
Okay. Another question? If no question, let's thanks again, Dr. At the end of the section of this afternoon, thanks all for attending this session and hoping to enjoy the conference, the following talks.